Hello, my name is Bakir Lacevic. I'm an associate professor at the Faculty of Electrical Engineering, University of Sarajevo. I'll briefly present the results of the paper co-authored with my colleague Dinko Osmankovic. First, I will describe the motivation and background behind our approach, which relies on so-called bubbles and burrs of free CSpace. The second part will focus on the main contribution of the paper, which is the structure we named the Generalized or Augmented Bur of free CSpace. At first, a definition of generalized Burr will be given, followed by a simple way to efficiently utilize burrs for CSpace exploration and path planning. In a nutshell, our main motivation is to avoid discrete or continuous collision checks of candidate local paths, but instead use the distance information from the robot workspace to build solution paths that are guaranteed to be collision-free by construction. One of the first attempts to do so is the so-called bubble of free CSpace. Assume the robot in configuration Q with a minimum distance dc from the set of obstacles. The bubble B of Q is the set of all configurations Y such that a certain CSpace metric rho sub B for Y and Q is less than dc. For a typical manipulator with rotational joints, the choice for this metric is a weighted Manhattan distance with coefficients Ri being the radii of cylinders, coaxial with joints and enclosing all parts of the robot starting from the corresponding cylinder all the way to the end effector. It is straightforward to prove that this metric is an overestimate of the displacement matrix rho sub r. Thus, it is guaranteed in conservative sense that, when the robot moves from configuration Q to configuration Y, no point on its kinematic chain gets displaced more than dc, which implies that no collision with obstacles can occur. Due to Manhattan nature of the metric, the bubble has a diamond shape and is very easy to compute. However, it is in general considerably conservative. A straightforward way to relax the conservative assumptions and thus increase the volume of the bubble is to use the original displacement metric rho sub r instead of Manhattan metric. The displacement metric yields the maximum amount in workspace that any part of the robot is displaced when moving between two configurations. As a result, we obtain the structure we call the complete bubble, which is larger than the original bubble. It may not be convex anymore, yet it remains stark convex by definition. Its main drawback is that it is extremely hard to compute, even for low degree of freedom manipulators. Fortunately, though, it's relatively easy to generate samples on its boundary, or more importantly, to compute the local paths, which are straight lines connecting the origin of the bubble with an arbitrary sample on the boundary. Such paths are collision-free by construction. The resulting structure, consisting of straight-line local paths, is named the Burr of free CSpace. The name Burr stems from the resemblance to the spiky flower of burdock plant. As it was shown in our previous work, to compute the Burr, we only need a single distance query and several forward kinematic computations. Formally, the Burr can be defined as an intersection between the complete bubble on one side and a set of rays originating from the configuration Q. The directions of rays are determined by the set of remote points that are usually chosen randomly. The construction of Burr reduces to the computation of individual spines of the Burr. This is equivalent to the following problem. Given the current robot configuration Q, a distance dc, and a remote configuration QE, move as far as possible along the ray QQE starting from Q until some point on the robot gets displaced exactly by dc. We solve this problem through iteration process by advancement of scaled ordinary bubbles. It is worth pointing out that this procedure converges rapidly and requires only the computation of forward kinematics. No additional distance queries are necessary. The technical details can be found in our previous work. Here we have a side-by-side comparison of RRT and RBT. The mechanism of RBT is very similar to that of RRT. However, instead of attempting a single extension from a given node toward the random configuration and subsequently checking it for collision, RBT grows a Burr from that configuration. As a result, we usually have a faster exploration of free CSpace. A natural question arises whether we can acquire more knowledge about the free CSpace. More precisely, can we further propagate the spines of the Burr, possibly in the same direction? A naive way to do so would be to have another distance query at the end of each spine, compute a new spine, and attach it to a previous one. Thus, we obtain the structure called Generalized or Augmented Bur. Clearly, such an approach would be computationally very expensive, since it would require many distance queries. However, under the assumption that the environment is decomposed into a set of convex obstacles, we can successfully tackle this problem. Assume the robot is in configuration Q, and let's observe a jth link denoted by PQ and ith convex obstacle WOI. Now, the distance query provides us with the minimum distance, but also with the pair of closest points, point N belonging to the obstacle and point A belonging to the link. It can be proven that the plane AIJ passing through point N, perpendicular to vector NA, completely separates the obstacle from the link. Once we have points N and A, we can write the equation of the plane. Moreover, the distance between the link and the plane is identical to the distance from the link to the obstacle. Now assume the robot moves from the configuration Q to the endpoint of the spine. As a consequence, the link PQ gets relocated to position denoted by segment P1Q1. From the properties of the Burr, no point on the link gets displaced more than the initial distance between PQ and the plane. Now, instead of calling another distance query to compute the distance from P1Q1 to the obstacle, we can simply find the distance from P1Q1 to the plane, which is trivial. After minimizing these segment-to-plane distances over all links and obstacles, we can use this cheap distance underestimate for further propagation of the Burr. Interestingly, we can repeat this procedure until it converges, meaning that the link finally hits the plane, or until we reach the given number of iterations. Apart from the initial distance information, no further distance queries are required, only the forward kinematics and trivial point-to-plane distance computation. This procedure assumes the robot link is a thin segment, however, the approach works for any polyhedral representation of links. Here we have the examples of generalized Burr for 2 degrees of freedom and 3 degrees of freedom planar robots. On the left, there are 4 generalized Burrs corresponding to 4 different configurations for a 2 degrees of freedom robot depicted below. The Burr is colored black, while the additional extensions within the generalized Burr are colored green. Clearly, the generalized Burr captures substantially larger chunks of free CSpace. On the right, we have an example in CSpace filled with obstacles corresponding to the 3 degrees of freedom planar robot illustrated at the bottom. The original bubble is colored blue, the Burr is colored black, while the generalized Burr is colored green. Here we have the side-by-side comparison of RRT, RBT that uses ordinary Burrs, and RGBT that uses generalized Burrs for tree expansion. This example shows the scenario where obstacles do not occupy much CSpace. Further, we have a more complicated scenario with cluttered space. Again, we can see that RGBT explores the CSpace much faster than other algorithms. Finally, we have a side-by-side comparison of algorithms for a scenario involving narrow passages. Once again, we clearly see the exploratory capabilities of RGBT. It is worth pointing out that the RGBT algorithm is very simple in structure and requires only basic procedures: distance query, nearest neighbors, and forward kinematics. No heavy preprocessing, learning, nor complicated data structures are necessary. We conducted several case studies involving different types of manipulators and different types of environments. The performance gain with respect to RBT was ranging from 50 to 90%. The performance was exclusively related to averaged runtimes. The algorithms are implemented in C++ using the FCL library for collision checking and distance queries. It is important to state the limitations of the approach. First, the current algorithm assumes that the environment is decomposed into convex obstacles. Moreover, we observed that the performance gains decrease when the number of obstacles increases. We are currently addressing this problem by exploiting the underlying decomposition of obstacles using bounding volume hierarchies within FCL library. These bounding volumes are inherently convex, and thus the need for initial explicit convex decomposition can be relaxed. Furthermore, RGBT algorithm provides only a feasible solution path within static environments. There is an ongoing research to develop asymptotically optimal version of RGBT together with the version capable of replanning and hence dealing with moving obstacles. Moreover, we are working on development of the OMPL implementation of the algorithm. Other interesting open questions that could be addressed are the problem of oversampling and the development of kinodynamic version of Burrs. Thank you for your attention. The authors will be happy to address any comments or questions.